All right, we have here another fluid dynamics problem. I like this problem because it has practical implications and it's fairly common in the world, and that is that it's a siphon, which is I define here as a device for removing liquid from a container. So siphons are kind of a cool thing to understand, and Bernoulli applies to them, of course, in a really cool way. And in this particular problem, we're given this tank of some kind of liquid. The density of the liquid's given, and then there's a tube there that is removing liquid from the tank. So um, let's go ahead and assume the container is really large here. The language of the problem doesn't tell us that, but it also doesn't give us the radius of the container. So if you're given the radius of the container, that's a really clear signal usually that you're meant to consider the kinetic energy of the fluid flow as, say, the level would go down in the container here if as we're siphoning the fluid out. And if you were doing this in some kind of, highly technical way, you probably would consider that, unless it was from a lake or river, something like that. But in a case like this, you probably would. But here, again, just to kind of simplify our world a little bit in this problem, we're going to assume that this is a really large tank. So I'll say here, it's a large tank, so much so the radius of the tank is so much greater than the radius of the tube that the velocity of the water as it is, say, descending down the tank is so much smaller than the velocity in the tube that it can be considered negligible. What I usually use as a general rule for that when students are wondering, like, how do I know? Is I'll say, is it two, if it's 2 orders of magnitude or greater different, that, smaller or larger, then you know that you have a big enough difference there that the smaller one you can consider negligible. Okay, so we have some choices here of different points to compare, and you're given even these nice little labeled A, B, and C points on the tube. And a point that's often forgotten is the surface of the tank, right? The surface of the water. So I would say if you have like another point that you know something about in the problem, like in this problem, the surface of the water, then label that too, right? So you could call that like your point D if you wanted to. Or you can just call it the surface because it is easier to describe than that. So the first thing I'm going to do is compare surface of the water to point C by Bernoulli. And you might wonder, why is she choosing point C? I really could choose any point I wanted, but I'm going to choose point C because I'm going to put my y equals 0. That's the lowest elevation in the problem there. So I'll set my y equals 0 to that lowest elevation there. Um, so again, for this particular problem, there's definitely more than one way to solve it. Still, we got to try something, right? So compare surface versus point C, again, using Bernoulli. For the surface of the water, I know that I have atmospheric pressure, right? And my kinetic term is going to be 0. We're told the tank is large, so I don't have to worry about that. Rho is given. G. Now, what's the elevation of the surface of the water? Now, I look at where my lowest elevation, that's my y equals 0. So the water surface elevation in this problem is H2 plus D. So the notation in this problem is a little bit bulky, but you don't always get to control that. So kind of go with it. And then I'm going to set that equal to now looking at point C, and that's going to be atmospheric pressure. Now, point C does have a kinetic term, 1/2 rho. I'll call this V sub C right now, squared, and then no gravitational potential energy term. So actually, it might be helpful for me to do it this way, to say, all right, this term over here is the term of the surface of the water, right? This term, and this term right here is at point C. And those are the 2 points that I'm comparing to one another. Great. So if I put these 2 equations together, then I'm able to solve for V sub C. I get that V sub C is equal to the square root of 2G H2 plus D. So that gives me something, right? The speed of the water at point C. So now, so I compared those. I'm not done. I need to keep on comparing some points, right? I'm going to now compare points B and C. You might be wondering why I'm comparing those two, but we'll talk more about that as we go. You can again compare whatever points you want. And sometimes you can just kind of say, all right, I'm just going to keep comparing points, different points, and generating equations until I have enough equations to solve for what I want. Sometimes that's what you do. So now let's compare points B and C. So point B is going to be pressure at B. That's now not atmospheric pressure, notice, because that's now inside the tube. The tube is not open to atmosphere up at point B. So I just have to call that piece of B and go with it. I don't know what that is. Plus 1/2 rho v sub b, the speed at point B, squared, plus rho g, now the elevation at point B. And that elevation is h1 plus h2 plus d. So all of this here is point B. And then I'll set that equal to, again, any 2 points in the system, point C, which is going to be atmospheric pressure plus 1/2 rho VC squared. And this, oh, I could say here plus 0. That's point C. Okay, now is when we're going to pull out something kind of useful. Now, think about continuity equation, right? Equation of continuity. If you need a reminder on that, pause this video and go back and review the equation of continuity. An equation of continuity basically reminds us that as long as we have only one way in and one way out of a tube or like some kind of fluid system, that our volumetric flow rate is going to be equal everywhere in that system. And if I look at this tube, the tube that goes from A to B to C, there's only one way in and one way out in that tube. So I know that I can use equation of continuity in that tube. So what equation of continuity tells me, it tells me that the area at B times the speed of the fluid at B is equal to the area of the tube at C times the speed of the fluid at C. Now, this is just a uniform tube, right? I know I don't have it drawn that way, but this is just a uniform, like say plastic tube that you would use for water or something, like a hose or something. So what that tells me is that AB, the areas are equal. And if the areas are equal and the flow rates are equal, that tells me that the speed at B is equal to the speed at C. So their speeds will be the same. That might make sense to you if you think about fluid being incompressible. That's like water, right, being incompressible. And that if the hose had to be filled with fluid to even start this, right? It had to be filled with liquid to even start this. So whatever speed the liquid will have at point C, it must have that speed everywhere along the tube, all the same speed. A way to picture this, sometimes if students are having trouble with this, is you can consider the hose to be full of like little marbles or something like that instead. And as long as all the marbles are in contact, right? There's no like gaps, the speed of one marble will be equal to the speed of any other marble along that tube. Okay, so I know that those are the same, so I'm just going to start calling that V now. I don't have to use the subscript. I can drop that subscript, which is kind of nice. So if I drop that subscript and I know that those V's are the same, then that's going to tell me that actually those kinetic energy terms are exactly the same on either side of the equation. So those can go away. And that allows me to write an expression for the pressure at point B is going to be atmospheric pressure minus rho g H1 plus H2 plus D. So this is another equation that I might find useful. For part B too, I guess our answer for part B here is what is the pressure in the liquid at the topmost point B, right? But so this is why I would set it up and solve for this particular thing. But I'm also just trying to show you in general that no matter what the problem is asking you for, your general process in these Bernoulli problems is to compare points that you know something about. All right, so we've got our part A. Let me kind of label these. Our part A is answered. Our part B is answered. And then this last part here asks us, theoretically, what is the greatest possible height that a siphon can lift water? And I'm going to kind of leave that one to you. I think that's an interesting question. You can solve that numerically, like in our gravitational field using water, right? If we say that we're now talking about water, and the density of water is something that's known here. If you're, say, taking water out of a swimming pool or something like that, so this is a real application question. What is the greatest possible height that the water could be lifted? So you can think about how you could answer that, like what must be going, the key there is what must be going on in the tube at B, and what conditions do you need there in order to continue to have water flow from the tank out through point C?